So kind of like in the old days, like I forget if it. I think I might have the kind of database that actually fits like this. There's this shared everything storage. So essentially, you can imagine like workers at their computer, or you with your laptop, right? And each one of these things essentially represents a different laptop. And each person's laptop is essentially querying a pool of resources that are all sitting on one computer. Okay? So when we say node, we really mean like a computer. All right. So you can see that each one of these things, like our laptop, each has the memory, CPU, and disk. And then when we query the database, right, we're querying a pooled resource where the CPU, memory, and data, all the data is just in one location. So because all the resources are sharing everything here, right, this is called shared everything storage. Okay. And that was kind of like the first way that these databases, like these kind of analytics databases, were architected. Eventually, because eventually what happened was they moved to more of like this shared nothing. Let me show you how that works. This is called shared nothing because if you want to query a record, it's and the record lives here. You querying something over here is not going to affect the resources in a separate location. Okay? So in this case, obviously, if someone's querying, records over here, because the CPU and memory is shared, right, we have a bottleneck. Okay? And what that means is as we have more data, right, we would ideally like to scale this, but that's not necessarily scaled automatically. And because of that, right, we're kind of like susceptible to bottlenecks as the data increases. So in this case, right, instead with this architecture, you can see that we can add more nodes, right, as we have more data. And what's occurring, if we kind of zoom in on this, is, maybe I can show it better here. It's about the same, is that our records are split across, 4 different computers. And this allows us to then query our records in parallel. Okay? Meaning that if I want to find, say, the average year of movies in our database, well, we can get the average of each one of these nodes. Okay? Collect, say, like the average is 1992 here, and 1995 here, and 2000 here, right, and 1980 here. We can take the average and essentially do like a weighted average, meaning we weight it by the number of records, right? And then take the average of that. Like from getting the average back from each one of these nodes, we can then compute a final average, okay? So here we're doing a couple things, right? One, called like partitioning our data, right? It's spread out across different computers. Notice that like this is how Redshift is organized, by the way, and this is considered like an upgrade because it's kind of like smoothed out, right? We have resources for each a set of records, and we can perform the operations in parallel. Okay, so as our data increases, we can add more nodes, right? And that means that as we add more nodes, we're adding more compute power and and like memory, and that's scaling as our data scales. Okay. These nodes here, it's kind of like has a name. So if you think about querying this database, you issue a query to the leader node. It's kind of like the brain. Okay. And the leader node is then telling each one of the compute nodes, hey, I need you to calculate the average on your partition of the data. I need you to calculate the average, right? And then these averages are then sent back to the leader node to finally get that final average here. This procedure is called map and reduce. All right, you may have heard of that. Okay, the map part is 4 different nodes all doing the same thing, right? We're like having this operation be performed in parallel across 4 different machines. That's the mapping. Calculate the average, calculate the average, calculate the average. The reducing is from these 4 averages, reduce this to 1. Okay? And you can do this, as you imagine, with like any kind of queries. Find the movies after 2000, find the movies after 2000, find the movies after 2000, etc. Then reduce it, combine them all together. Okay, so that's all really map reduce is. It's You probably have heard of that, but that's really all it is. And this is the way that Redshift is organized, is with like a leader node and then different compute nodes. Okay. One thing, now this is kind of like the standard way. Like Redshift was considered like the way, like the best like analytics database for a while. Snowflake is organized differently than this. One thing that's like challenging about this is, or one thing that's maybe not ideal about this is, as you get more data, you're scaling memory and CPU, right? We kind of talked about that. Now that might seem like a good thing, but what if only one, like we rarely query this database. So now this database is running the whole time, and we want to store all our data, but we actually don't need all this computing power, as opposed to if 10 people are querying the database simultaneously. At that point, maybe you do need more computing power. Maybe like a lot of this data, we only really need like a few records from it, but we want to store all the data. Essentially, the point is that it's not the case that as you scale data, your kind of computing, and especially your computing resources, that requirement scales at the same rate that your data scales. Okay? And in terms of expense, this storage is not expensive, but CPU power generally is expensive. So if you're just storing more data, but because you're storing more data, you have to pay for more CPU, right? That's inefficient. So that's the point, is that hey, all right, I do want to store all my data here, but I don't need more CPU resources. In that case, Redshift does not really allow you to get around this, right? But Snowflake does. So with Snowflake, we're kind of, now you're familiar with it, that we have these warehouses, right? And that's our computing power, okay? And then you have a storage layer. So we are here, this is called isolated compute, because you can imagine the storage layer is just like files, right? Just that just sit on S3, and that we are accessing those files, okay? So as we get more data, we can just purchase more storage, and we're not necessarily expanding the amount of compute to go along with it. And you all saw this when you set up a data warehouse, right? And you said how large you want the data warehouse. That was not dependent on the amount of data that you're storing. So this is why this can be pretty optimal, because you can just store data, not worry about it. And the way Snowflake works, you're effectively just paying for your queries, for the amount that you are paying a little something for storage, but a lot of it is dependent on how much CPU power are you using. Okay. This services layer, say you want to restrict who can access which database, right? We saw this as well. That's taken care of in this services layer. I think it's like a pooled resource from Snowflake, but it's considered like a different kind of layer. This thing here, this is what's issuing the queries, right? You might have a different data warehouse for each department, like marketing or analytics. This way we can keep track of their costs and things like that. And then the services layer is going to say, hey, the marketing department is able to access, maybe this marketing data, but don't let them access, the employee data, right? And that's taken care of in the services layer here. The other thing you see here is the query manager, right? Snowflake is optimizing the queries. When you issue a query, it's trying to perform it efficiently. This services layer helps take care of that, things like that. Okay. So this is one of the reasons why Snowflake is preferred by some organizations, is that it's cheaper. It can be cheaper, right? Because as your data expands, you're not paying for more compute, whereas here you are. Okay. We have to add more nodes, and with adding more nodes comes this overhead of memory and CPU, and that's the expensive part. Cool. So that's the main thing I wanted to go through. We have this stuff, I would say do these readings. I think these are good for interview questions and things like that. And then the next thing I would do is, I'd say these two problems, if you haven't done them, let me put these towards the end. The seasons problem, I do like this as a Python problem. And then this SQL assessment is good. This is part of the same exam or the same take home that we saw here in this refactoring SQL. So if you haven't done these, right, move through these. This one hasn't been deployed yet. Okay. Cool. So I'll put you questions about this, like those three kind of different models, right? The shared everything,